We're going to start with graphing the what we call the parent function sine of x. I'm going to come up here and make a little mini unit circle. All right, so remember that your sine value is your y value on the coordinate plane because it's coming from opposite over hypotenuse. So at 0, the sine is, call it out everybody, at 0, sine is 0. Up at pi over 2, the sine is 1. At pi, the sine is, at 3 pi over 2, the sine is, and then back at 2 pi, the sine is 0. So we want to come plot those 5 points on our graph. So we're going 0, 0. See, your graph is marked off. There's pi over 4. Here's pi over 2. So pi over 2 is 1. Pi is 0. 3 pi over 2 is negative 1. And back up to 2 pi is 0. And the sine function is a curve. There's going to be no straight line. So we're going to come in here and it makes a hill and a valley. All right, so now we're going to go over to our unit circle. And we're going to measure in negative angles. So we're going to measure clockwise. So if I go to negative pi over 2, I'm here. So my sine is negative 1. So at negative pi over 2, my sine is negative 1. If I'm here and I go to negative pi, my sine is 0. If I'm here and I go around to negative 3 pi over 2, my sine is 1. And if I'm here on my unit circle and I go around negative 2 pi, my sine is 0. So again, there's a hill, there's a valley. So that sine wave, it's continuous, right? And we have these repeated cycles, okay? So let's talk about a few things. What is our domain? All real numbers. We're going to write our domain in interval notation, so we're going to go from negative infinity to positive infinity. What's our range? Negative 1 up to positive 1. In brackets, because we include those endpoints. You are correct. All right. With sinusoidal functions, we want to talk about the amplitude. And the amplitude is half the distance between the minimum and the maximum. So if the minimum's here at negative 1 and the maximum is up here at positive 1, that's a distance of 2, and half of 2 is 1. So this has an amplitude of 1. And then the other main thing that we want to look at with sinusoidal functions is the period. The period is a length along the x-axis. How long does it take one wave or one cycle of the function to complete? So if I look at, I start here and I go up and I go down and then I go back to start. So how long did that take me along the x-axis? 2 pi. So those are the key characteristics of a sinusoidal, that's the parent function. And then we're going to see that we're going to do some different things and how this function transforms. All right, the one thing related to the amplitude is our midline. A midline is nice because it means exactly what it says. It's a line that's going to cut through the middle of your graph. So you may want to grab a colored pencil. The midline goes right through there, and it cuts your graph in half. And so this midline is at y equals 0, because it's a horizontal line. All right, so now we're going to do a new function. Here's our function, sine of x plus 1. So here's what I'm going to do. First, I'm going to come with my regular pencil, and I'm going to graph the parent function, sine curve. So sine goes through 0. At pi over 2, it reaches to 1. At pi, it goes through 0. At 3 pi over 2, it goes to -1. And at 2 pi, it goes back to 0. It makes a hill and a valley, and then it does the same thing on the other side. And we make a hill and a valley, and that's the parent function. I'm going to put as y equals sine of x. But now with my colored pencil, I want to graph y equals sine of x plus 1. So if I come in here and plug in a 0, the sine of 0 is 0, plus 1 is 1. If I plug in a pi over 2, the sine of pi over 2 is 1 plus 1 is 2. If I plug in a pi, the sine of pi is 0 plus 1 is 1. If I plug in a 3 pi over 2, the sine of 3 pi over 2 is -1 plus 1 is 0. And if I plug in a 2 pi, the sine of 2 pi is 0 plus 1 is 1. Do you see if I compare my two tables, what happened to my outputs? Did all of my output values do what? They increased by 1, right? So my output, which is on my y-axis, increased by 1. So if I come and I graph my points, at 0, I'm at 1. At pi over 2, I'm up to 2. At pi, I'm at 1. At 3 pi over 2, I'm at 0. And at 2 pi, I'm at 1. So I make a hill and a valley. So what happened to my sine function? It went up by 1. What do you call that when it goes up by 1 like that? It's a transformation. What kind of transformation is it? Okay, the plus 1 is what caused that transformation. You know what we call it? A vertical shift, you can call it, or a vertical translation. Translation is one of your transformations, and I always remember it has an SL because it slides. On a vertical shift or vertical translation, the whole thing just slides up 1. And we went up 1 because it had a plus 1 after the sine of x. So what's going to happen to these points? They're all going to go up 1 also. So you could go to this point and just go up 1, go to this point and go up 1, go to this point and go up 1, go to this point and go up 1, and there's the other side of your sine graph. Okay, now let's just talk about our key features. Did the domain change? No, the domain is still all real numbers. Did the range change? Yes. What's our new range? How low does this graph go? What's the lowest point on the graph? The new graph. The lowest point on the new graph is a 0. What's the highest point on the new graph? 2. Okay, look, compare the range of the parent function with the range of the new function. Do you see that it went up 1? Because we're doing a vertical shift and the range measures your y values, your output values. So do you see that connection? All right. Did our amplitude change at all? Your amplitude goes from the least to the greatest. So how many spaces are in here? 2 spaces. And then you cut it in half. What's half of 2? 1. The amplitude stayed the same. The amplitude is still 2. Amplitude stayed the same. But what about the midline? The midline is going to shift up with the graph. So the midline is now going to be y equals 1. Get another color and draw in my midline here. The midline is at y equals 1. So notice the amplitude did not change because we just shifted it up, but the midline shifted along with the graph. So since the graph translated up 1 unit, the midline translated up 1 unit also. Does that make sense? All right, we're going to go to the next one. And we're going to start by graphing the parent function for sine. Sine starts at 0, goes up to 1, goes back to 0, goes down to -1, goes back to 0. Sine makes a hill and a valley, and then it does the same thing on the other side. And we have a hill and a valley, and that's the parent function y equals sine x. All right, but now here in my table, I have a new function. I have sine, and then notice parentheses, x plus pi over 2. So notice up here in this function, the plus 1 came after the sine of x. So we plugged into x, we took the sine, and then we added the 1 at the end of it. This time, we're going to plug into x, we're going to add the pi over 2, and then we're going to take the sine. So you see how the order is different? All right, so if I plug in a 0 here, 0 plus pi over 2 is pi over 2. And what is the sine at pi over 2? Sine of pi over 2 is 1. Does that make sense to everybody? So now I'm going to plug in a pi over 2. I'm going to do this addition first. Pi over 2 added with pi over 2 would equal to pi. So what's the sine of pi? The sine of pi is 0. All right, so if I take a pi and I plug it in, I'd have pi added with pi over 2. That would be 3 pi over 2. What's the sine of 3 pi over 2? -1. All right, if I plug in a 3 pi over 2, 3 pi over 2 added with a pi over 2 is 2 pi. What's the sine of 2 pi? 0. Now if I add in a 2 pi plus a pi over 2, so let me just go to my unit circle. What's going on? If I go around 2 pi and then I add another pi over 2, I'm going to be right here, right? So what's my sign? 1. So let's go graph those points. At 0, I'm at 1. And at pi over 2, I'm at 0. And at pi, I'm at -1. And at 3 pi over 2, I'm at 0. And at 2 pi, I'm up to 1. So I'm going down a hill, make a valley, and go up a hill. Let me add one more point that might help some of you have a better picture. Let's plug in negative pi over 2 right here. If I plug in negative pi over 2 to my function, negative pi over 2 added with pi over 2 is 0. What's the sine of 0? So I'm going to come cover up this part right here. Can you see what happened from my parent function, which is in regular pencil, to my new function in orange? What happened? Which way did it go? We did a shift, right? You see if we went to the left? Do you see here if you went to the left? Did we shift left? Okay. How much did we shift left? You're shifting on your x-axis, right? How much did we shift left? How many spaces is this? Right, from here to here? 2 spaces, which is worth how many on my x-axis? Pi over 2. This is a horizontal shift, or a horizontal translation, and we went left pi over 2. All right, do you remember about horizontal shifts from Algebra 2? Now, some people think, oh, on the horizontal, it goes backwards because the rule for the horizontals is sine of x minus h. So when I have x plus pi over 2, that is really, I can think of that as the sine of x minus a negative pi over 2, because minus a negative comes out to be plus. So when I have x plus pi over 2, my shift is really a negative pi over 2. That's what makes it go to the left. All right, compare it to the parent function. Is the domain the same? Range is the same. What about amplitude? Midline? All those things stayed the same, right? What about your x and y intercepts? Did those change? Yes. So when you do a horizontal shift, the intercepts will change, but the other things will not change. All right. We're going to go to our last sine graph. We're going to start again with the parent function. You're going to be an expert at graphing sine graphs, yes? Sine starts at 0, goes up to 1, goes back to 0, goes to -1, goes back to 0. Sine makes a hill and a valley. And then it does the same thing on the other side. All right, but now our new function is going to be y equals 2 multiplied by sine x. So let's think about our order of operations. We're going to plug the 0 in. We're going to take the sine, and then after we take the sine, we're going to multiply by 2. All right, so let's work it out. Sine of 0 is 0, and 0 times 2 is still 0. Sine of pi over 2 is 1, and 2 times 1 is 2. Sine of pi is 0, and 2 times 0 is 0. Sine of 3 pi over 2 is negative 1, times 2 is negative 2. Sine of 2 pi is 0, 2 times 0 is 0. Let's plot those 5 points. All right. So now we're going to trace our sine curve. This is going to make a taller hill and then a lower valley. So I'm going to go to the same places on the other side. All right, is our domain the same? Yes, right? It's a continuous curve. Your domain of your sine function is always going to be negative infinity to positive infinity. It's continuous. But what happened to our range? What's the range now? Negative 2 to positive 2 with brackets because we're including it. What is our amplitude now? The amplitude is now 2 because we take the average of negative 2 to 2. That's 4 spaces. Cut that in half. Your amplitude is 2. So your amplitude is this much right here. This distance is the amplitude. It's halfway between the maximum and the minimum. And your amplitude is always, always positive. Where's your midline? That's still at y equals 0. What kind of a transformation do we call this? This is a vertical stretch. Vertical stretch by a factor of 2. I'm just going to say by 2, but it's by a factor of 2. Look at the difference between the vertical shift up here and the vertical stretch. The big thing is to notice what happens on the zeros. What happens when you multiply something by 0? It's still a 0. So these zeros are still in the same exact place. Do you notice that? But it's these points that get stretched. They stretch up and they stretch down. Right? They're stretching both directions. But up here, when we do a vertical shift, we're adding 1. So everything went up 1. Even the things that were on a 0 went up. So you notice the difference between those two. All right. Now, notice where this number is right here. Do you see the 2 is in front of the sign? So when we have y equals a times sine x, that a is always going to cause a vertical stretch. So if it was a 3, it would be a stretch by 3. If it was a 4, it'd be a stretch by 4. But what happened if that a was a 1/2? A vertical compression, or we sometimes use the word vertical shrink. If it was a 1/2, instead of going up to 2, this point would shrink down to 1/2, right? But it's this multiplier right here that causes vertical stretches and compressions. All right, I'm going to pause here.